Hi everyone, thanks for joining. We'll start on top of the hour. And let me start sharing my screen in the meantime. All right, it's top of the hour, so let's go ahead and get started. My name is Julia Matevosyan. I'm an Associate Director and Chief Engineer at Energy Systems Integration Group, or ESIG, and I would like to invite you to the 7th session of the Forum for Implementation of Reliability Standards, or I2X First, which is funded by Department of Energy and supported by us. Let's go next slide. So yeah, some rules of conduct, you probably all know. So the first half of the meeting will be recorded. So this is presentation part and will be posted on ESIG website. And if you do not wish your voice to be recorded, please do not speak during the call. If you don't wish your image to be recorded, turn off your camera. And let's go ahead to the next one. So if you just joining first time for i2X First, the goal here is to facilitate understanding and adoption of new and recently updated standards relevant for existing and newly interconnected inverter-based resources. We convening industry stakeholders here to enable practical and more harmonized implementation of the standards. As I mentioned, we record the presentation portion. We also produce a summary of each meeting where we're capturing recommended best practices, challenges, and gaps that require future work. So just a little bit about leadership team. We have Cynthia Bothwell, who is a contractor for DOE. Robert Reedy, who is also a contractor for DOE, Will Gorman from Lawrence Berkeley National Laboratory, Jens Bermer from Electric Power Research Institute, or EPRI, myself from ESIG, and Ryan Quinn from Elevate Energy Consulting. So just to recap from the last meeting, the previous one was on challenges with IEEE 2800-2022. Adoption and planned revisions. Andy Hoke provided an update on 2800.2 status, kind of where we are. And then we talked about potential areas and issues for improvement for forthcoming IEEE 2800 revision. So Manish Patel kind of walked through the known or identified issues during IEEE 2800 implementation that can go and be revised in the next round. Then we talked about forthcoming IEEE project authorizations, including new grid forming interconnection requirements as well that we'll be working on. And Jens presented on that one. And then as usually we had Q&A and structured discussion. As I mentioned, meeting summary, recording and presentation all has been posted now. And I believe you can see a link in the chat to go where the information is. So just a few key themes from the last meeting. IEEE 2800 is progressing towards publication. The initial draft of the document received 87% ballot approval, and we got 800 comments to address. Primarily, the comments were about unit level testing and design evaluation, and we addressed the comments, reballoted it, and the ballot received 95% approval. So it happened after the meeting, but just to provide this update. We need to balance prescriptiveness of the recommended practices versus flexibility in testing and design. So the latest draft, based on the comments that we received, tightens tight testing requirements, but it gives flexibility for design and commissioning evaluation. So it's like is less prescriptive and less quantitative criteria in those two areas. With regards to lessons learned from IEEE 2800 2022 implementation, there were some identified issues where clarification is needed, and specifically with regard to reactive capability, voltage reactive control modes, and write-through definitions. And so all of these misinterpretations and complexities will be shaping the next revision of the standard. So we are basically picking up a list of issues that we will work on when revising IEEE 2800. Then there are, as I mentioned, forthcoming grid forming focused efforts. There will be parallel work, which includes P2800A. The idea is to remove barriers from IEEE 2800 standard that prevent grid forming adoption. Then there will be a new document that we'll be working on, 2800.1, which will be equipment level, so inverter level grid forming requirements. And then there will be full 2800 2022 revision. So there will be a new updated version of the standard after this effort. We talked about global alignment and regulatory education. So there is this effort to align IEEE and IEC standards. So this coordination still remains aspirational, but we all understand that harmonization lowers the cost of equipment and complexity of implementation. And regulators need better education on evolving technical standards and understanding why the standards are important, why harmonization is important, and what does it all kind of leads to. And then we would like to invite everyone to participate in this IEEE IBR Interconnection Working Group, which will be working on all of the standard revisions that I just mentioned. And so if you're interested to join, please just reach out to me and you can join the working group and work on the standard, help us with language development. This 2800 series is expected to be a living framework, and as we learn more integrating inverter-based resources into the grid, it is expected that the standards will be updated on a regular basis. So just to show where we are on i2X first, season 2, as I mentioned, we're in the 7th meeting today. We'll be talking about change management during IBR planned interconnection process and commissioning and how to maintain conformity as projects are changing hands. And ownership. And then the December meeting, we're planning on IBR plant commissioning best practices. This is kind of a big topic, so it may take 2 meetings, but we'll see, what kind of feedback we're getting. Do we need another meeting, or maybe we'll focus on a different topic? And if you feel like, we are missing a topic and we need to cover something else, please reach out to me with ideas. We are open and flexible. And just before I jump on the agenda for this meeting, I just wanted to talk about this EMT trainings that we have coming up. So DOE i2X effort also supports this EMT training initiative. So with that, maybe some of you have attended ORNL workshop in October, in October, with which ESIG also supported, and there was some tutorials on EMT provided there. The next training that ESIG is organizing is happening mid-December. You can see QR code now. I believe we still have some openings. So the idea is just to have this 3-day training to enhance knowledge and ability of current workforce to perform EMT simulations. So we'll focus on practical methods and best practices to leverage EMT, and focusing on integration of inverter-based resources. The idea of this training, it will not be hands-on training. It's more of a kind of talking about EMT studies, EMT modeling, and then there will be demonstrations that the trainers will provide, and you'll be able to see kind of how to carry out the studies, but primarily also focused on the results and what to look in the results. This training, once convenient, the training is in person. Once conducted, it will be all posted online, so you can watch it as well. Yeah, if you're interested to attend, scan the code and register. Then we have more training opportunities in 2026 coming up. And I have a list on this slide. I will not read through this, but basically we'll provide more of EMT training focused on interconnection of inverter-based resources, model quality assessment, getting started with EMT software, and also deeper dive into EMT studies. Some of these trainings are in person and some of them are online, as marked on the slide. And then we just recently completed interconnection studies short course last week in Florida. So this course focused again, what does practicing engineer needs to know as they're working on the interconnection studies for inverter-based resources. All of the materials from the course are posted on our webpage, and you have QR code that will take you there. And again, you'll have the slides after this and can follow the links. So yeah, then now switching gears to today's meeting. As I mentioned, we'll talk about change management during IBR plant interconnection process and commissioning, and how to maintain conformity as IBR plants are changing ownership. This is a relatively common thing to happen, and we would like this change to happen seamlessly and conformity maintained throughout the process and lifetime of the project. So I'm almost at the end of my introductions here, and then we'll hear IBR developer perspective from Katie Iversen, Joseph Perry, and Andrew Lopez from AES. We'll hear OEM perspective from Miguel, Cova, Acosta from Vestas, and then EPC perspective from Patrick Hart from Mortenson. We'll hear all three presentations first, and then we'll have time for Q&A. But I will now already open Slido, so go to slido.com, event code first7, and you can start putting your questions to the presenters already as they speak. And then, as always, the second hour or 40 minutes, however much time we have left, we'll spend on structured discussion around these topics. So just some rules of conduct, be nice to each other, ask questions. This is what we're here for. And without any further ado, let's go ahead and get started. Katie, I turn it over to you.
Thank you, Julia, and thanks everybody for being here today on our holiday week to talk about this exciting topic. Today I have Andrew and Joseph here with me, and we are going to talk about our projects related to validating IBR settings during commissioning, specifically inverter settings. So there's just a lot of information we could do around a commissioning topic, and this is what we decided to really focus on today for you to learn from us. Joseph comes from our product solutions department. He works with our team to have products ready and know more about our products. And Andrew works on my team, which we do generator modeling and power system studies. So he is an engineer behind all of our work there. All right, so first we're going to go through background information. Why are these settings important? Modeling, UDM, EMT, and generic, and how that relates to our settings. Processes that we've worked on, OEM deliverables, commissioning, and settings comparisons, specifically with one example from the work we've done. And then takeaways. We know there's a lot of improvements we can do here, and we want to provide you with our ideas on those types of improvements. All right, so AES US business portfolio, just to give a little background from the types of work we see, we have a lot of operating assets. We have a pretty big pipeline. We have solar, wind, BESS, and so we're working with a lot of the manufacturers out there in all of these areas. So we see basically what a lot of people are doing around this material. All right, so first, why is it even important? Why should you even care about this? Inverter settings, if you read through the NERC disturbance reports, there's like a ton of them. Ryan always has them stacked on his slides. Basically, you can boil it down to a lot of them are this pie chart. Models and settings were aligned as expected, super small. We're not aligned and not as expected, always appears to be pretty big. So this is just like an estimate from looking through them, may not be entirely accurate, but this seems to be a pretty firm pattern in what they're seeing as they're investigating and what I saw when I would investigate these disturbances as well from the regulator side. It's important because of grid reliability. We all rely on the grid actually operating well. As developers, we don't have anything to connect to if there are issues around the grid in that area. And as planners or OEMs, grid reliability also impacts you. For us, a developer and owner, it's important for our project success to meet our commercial operation, which is very important to our financial structures and even operating the plant. In operations, it's important for your project success and continued compliance efforts. And I put productivity and resource management, but really I mean the sanity of engineers in general. There's nothing worse than spending a lot of time on an EMT model study, spending a lot of time with your manufacturer and your planners, everybody studying this thing, and then having some of the settings not be as expected. It's very discouraging. So the sanity of all of us here, resource management, so we don't all stand around and complain about it for way too long when we really could have fixed it at the front end. So I'll turn it over to Andrew to talk about the models.
Yep. Yeah. Thanks, Katie, and good morning, everyone. Yeah. So basically, right, we are talking about model settings that are not aligned and not as expected. And here's a nice visual that showcases the generic versus the UDM and EMT. So you can see the EMT and UDM is beautiful, and then the generic is very simplistic, right? And one of the reasons why is because interconnection requirements, they require generic models, and there's some validity to the generic models and some usefulness to them. However, it doesn't stop there, right? Because the generic models don't correlate or align very well with the actual equipment that's out in the field, right? And that's where the EMT and UDM models come in and step in, right? With the EMT and UDM models, you're able to relate closely to the equipment settings. So you know exactly what's actually out there, and you can actually study those particular settings prior to them even being inputted into the field, right? And their importance of the EMT and UDM models is, you have the requirements, performance, model simulation, and reviews already done up front, rather than you put in the default EMT UDM settings that are provided by the OEMs, right? And then you fine tune it in the field. It's just a recipe for not disaster, but a lot of stress, right? Trying to figure it out right before COD, and there's a lot of variability there. So the benefit to these EMT and UDM models and the detail up front give you that kind of assurances and de-risking of, hey, once I put it into the field, I have a high level expectation of how this plant is going to perform. And that's not what the generic models provide. So here in this slide, the high level inverter setting lifestyle cycle, right? It kind of gives a general path forward into, how do you get to that point where you are uploading your EMT and UDM tested settings, right? It all starts with your equipment selection and the project settings that you're going to predefine, which are usually aligned with the utility requirements, right? You also have to compare that against the OEM capabilities. Once you have that general idea of what you're working with, now you go into the project design and you start modeling all the other equipment and you start working with the OEMs to iterate and tune these inverter settings such that your plant can meet those types of requirements, right? Ride through is one of those. The other one could be like, hey, you need to recover after a fault, and you need to have maybe in certain utilities, it's like you need to showcase a grid forming response, right? And that's a iterative analysis, right? Because tuning, you can go into a tuning whirlpool and it's just, you change one thing to fix one thing and it creates another problem for another thing, right? So this is where most of the work comes in. Once you can get those tuning settings like locked down and it passes most tests, right? Most of the model quality tests and everything like that, right? Then, and it gets approved by the utility and the ISO, right? Ideally, nothing should change and you should be able to take those settings and commission those inverters on site with what you studied, right? And then once you've commissioned those settings on site, you can now go into plant operations. And if you needed to pull the settings from the plant after the fact, right, they should match with what you've studied, right? So this is the ideal inverter setting life cycle. Next slide, please. Okay, so this is a big effort over a long amount of time, right? Major parties involved across this project, or all projects, include, our stakeholders from transmission planners, planning coordinators, heavily with our OEMs, both inverters and our power plant controllers. We also have heavy involvement with our owner, like execution engineers, our interconnection engineers, to make sure that these settings are being implemented. We've also got our EPCs that are helping out with the design, and we have to coordinate with them to ensure that, hey, they're also aligning towards these requirements, right? And then lastly, our owner operations, we need to make sure we're coordinating with them so that they are also aware of what's being implemented out in the field, and they are also aware of what they need to get for us in the event that we need to pull those settings. And there isn't really a clear line of sight between all of these. It's basically each one of these circles overlap with everyone, as you can see in this visual. And they all have a way of impacting what those settings are, what the studied settings should be, and what the settings should be uploaded should be. So with that, I'll pass it off to Joe, who's going to go more in detail about our deliverables for the inverter OEMs.
Awesome. Thanks, Andrew. Thanks, Katie. And good morning, everyone. With that context from Andrew and Katie, we really want to dive into how AES is establishing our deliverables for our inverter OEMs across the entire AES portfolio. What we've started to experience a lot is that there is a high degree of variability across our OEMs in their models, in the platforms they're using, in the file types that make up those models, and in all that comes with the models, specifically the EMT models that Andrew was speaking to. And so AES is implementing ways of requesting deliverables so that we really get proper documentation of, approval of, and visibility into the parameters within the inverter on all of our projects. So you can see that these three buckets of deliverables kind of do map across a project lifecycle, especially as we get close into commissioning. A lot of this does have to do with that commissioning process once that model is tuned the way Andrew was describing. So starting with the inverter settings statement, this is a way for the parameters to be published after the model is studied and approved that it's going to behave the way expected in our contracts. And what it really does is it converts the extensive list of inverter settings that exist in OEM models into a very digestible list of settings that are high impact, such as ride-through settings or droop settings, in that realm of area where we really do care about how this inverter is going to operate in relation to our contracts and in relation to how the utility expects the plant to behave. So that all fits into the inverter setting statement, but then that last piece is the parameter mapping, where modeling is very important, but we also need to understand how those settings get from our EMT models to the inverters themselves and what that process is like. Are they the same names? Do they have the same values? How do you map something from the model into the hardware itself? Then we get on-site, and the parameters that get programmed on-site need to be verified. It's great and very important to model our plans, but if we can't verify that how something was modeled is actually how it is programmed on site, the model isn't much help. And so we're establishing processes with our commissioning engineers and with our OEMs who are helping us in commissioning to integrate ways to verify those settings into the existing commissioning process. Not only does this let us verify what is on site matches what was studied in the model, it's helping maintain our records so that we have better operational awareness once we finish commissioning. And then this last bucket, this is something that's ongoing that we're working to integrate and deploy on sites, but we're looking to integrate the inverter settings on site into our SCADA systems so that we have that operational awareness on a regular basis, that we know the inverter settings have not changed, whether from an operational mishap or for any reason. And it's just giving us that visibility on a routine basis that our settings continue to be the ones that were studied in the models. Also, we always have an eye to the future, and we think this really could create opportunity for alarms or historizing the data for study. And so once we can integrate our inverter settings into the SCADA system, it really could open up a lot of analytics and opportunity in that way with the data. So with those deliverables that we're expecting from our OEMs, how do we actually implement that into the commissioning process? Well, first and foremost, we're really trying to reduce the friction by identifying the key milestones for these deliverables and this verification. You can see the modeling studies up in that left-hand corner. That's the iteration that Andrew was talking about. While we're tuning and setting the model, we don't really care what those settings are. But once we have an accepted model, whether from the utility or between the OEM and us, once that model is accepted, we consider it as left. The settings should not be changing after that point. And so what we are requesting is this parameter statement from our OEM that we can then verify, it was an approved model, here are the settings, it's a one-to-one match. And then we go into the commissioning process. We understand commissioning is high-paced and very important and tight timelines often. So what's really important here is we're creating this underlying process that supports the commissioning process. It starts with that first upload. And you'll notice we upload them and then we immediately download them. That's to ensure that there's no loss of data or errors in that upload. It's great, upload the settings, but we need to make sure that nothing goes wrong in that upload and nothing gets switched. And I've identified some key opportunities that you might do in other downloads to verify across the commissioning process. I won't get into those because those are really project and utility specific. But what is important is as we get close to COD, we are again verifying that what is on site matches that verification from our as left model. And I wanted to highlight that we are doing this at AES. This is a quick screenshot of part of our commissioning process with, you can see the swim lanes for different engineering teams. And I won't go into depth on this slide in particular, but what I really want to call out is this purple and teal call out, where we are doing this process where we are downloading the settings from site, from the inverters there, and verifying them across that approved parameter statement to make sure that there's no discrepancies or changes that have occurred. If they have occurred, if we do identify discrepancies, we are able to quickly communicate that with our generation modeling teams and our OEM to understand why is there a discrepancy, seek correction, or get a clarification on why that discrepancy exists. So this is just a quick way to highlight that we are starting to implement this in our commissioning process with our commissioning engineers. So much so that I want to share a quick success story. I've kind of scrubbed this to make it more generalized and leave out any OEM specifics, but you can see here that here are some sample parameter settings that we would care about, the droop values, the ride-through settings. You can then see the values that were approved in that modeling process. Then we downloaded all those settings from site, and we're able to do a very quick verification to understand if there were any discrepancies. I then filtered it to show us only the settings that have discrepancies. Many of the other settings did not, so that's a great success. But really the success here is we were able to quickly identify these 5 parameters as ones that had discrepancies. You can see those bottom 2 settings were uploaded incorrectly. There was a mistake or an error that caused wrong values to go on site. But what's really interesting is those first 3 settings where one inverter has them all programmed correctly on site, and then the rest of them don't. And we need to understand, why did that happen? It doesn't seem like an error. It seems like that was done intentionally. And it turns out it was. That is the OEM's process when they're in commissioning to approach it that way. And so what this allowed us to do with this whole process that we've been talking about is quickly identify these discrepancies and then quickly seek resolution to understand, all right, why was there an error? Is it a big deal, or is this the way it's supposed to be? So I went through that rather quickly, but that is a quick success story about how these deliverables are impacting our commissioning process, because we identified these discrepancies, we're able to address them, understand them, and not delay the commissioning process, because we were able to give everyone on site the all clear that these are either expected or being corrected quickly. And I'll give it to Katie to wrap us up.
Thank you, Andrew and Joe. Okay, so longer term takeaways. During especially Joe's presentation, you're probably thinking, wow, that's like a ton of manual work. We're looking through a lot of different things. He mentioned a lot of variability by our OEMs, which makes this process difficult to automate. You're probably thinking AI. So here's the longer term takeaways. First, we suggest standardizing grid reliability settings and setting file types. This would be really important to automate easily with Python scripts, Excel scripts, AI eventually, or today. But it's really difficult to set these things up when all of our vendors, we're thinking like, I don't know how many vendors, like 10 vendors, all have different setting files and different areas where these settings are. Now, we don't expect all of the settings to be exactly the same because they're very specific to your device, but just some kind of standardization to where to find them, similar to what's happened in, the relay area. So we see that as really important to us to be able to be more efficient with what we're doing here. Improve the interconnection processes and reviews for the types of models that really go into the equipment. We see the need to have these reviewed, or we already see the industry going this direction with FERC Order 2023, with a lot of the new NERC standards, but we definitely want to see even more attention to this area by our planners and planning coordinators. For OEMs, access to inverter settings and setting change alerts, what we're talking about with SCADA, this is important to us. There's some OEMs that don't really feel that access to owners and developers is important. But to us, this is very important for maintaining our reliability. And we never want to be in a situation where there's an event and our plants have contributed and we can't quickly see what was on these inverters. And the programming both ways is important. What's going on, that's important during commissioning, but also being able to take what's coming off of it, take it off, and look at your model against it. That's where we're going in the industry as these events continue to occur, is event analysis. But the first thing you need to do with event analysis is have your model, have your settings, and just make sure it's even what you expected it to be. And then change management for firmware and software updates. EMT models are very detailed. There's a lot of reports about firmware, software impacting those versions. Sometimes we see settings are added, and that change management process, especially as our transmission planners and planners and planning coordinators have our model, is important to us to be more standardized and more work done there to keep our models up to date and our settings up to date. So those are the longer term takeaways, high level. There's a lot of other takeaways we could introduce, but these are the ones we wanted to focus on, especially because, you know, there's a lot of people listed here as industry stakeholders that would need to support this type of work. Right now, it's very manual. It's very clunky. We're pushing OEMs to support us in this area. We get a lot of different levels of support. And we also see that sometimes what is presented as this is what our manufacturer does is not always the experience that we're getting boots on the ground working with the inverters or with the equipment. So with that, I think we'll turn it over to the next presenter.
Thanks so much, Katie, Joe, Andrew. Let's move on to Miguel, and we hear OEM's perspective. And again, I would like to encourage everyone to put your questions in slido.com event code first7. Go ahead, Miguel. You can share your screen now. Miguel, your screen is coming up, but we cannot hear you.
Can you hear me?
Yes. Yes,
Okay.
now I can hear you. A little bit faint. Maybe you can speak up just a little.
Okay. Well, we'll have to turn off the video. Okay, can you hear me now?
Yes.
Is it better? Okay. Okay. I guess it's in full screen, right?
Yes.
Okay, cool. I'll start. Well, thank you, Julian. Very nice presentation, Joe, Andrew, and Katie about the challenge you experienced. I will try to complement this with the perspective from an OEM, from Vestas, and where do we see actual challenges during the whole lifetime of the life cycle of a project when we talk about change of management of the IBR plant. I'll try not to focus too much. I don't want to sound like a broken record on the alignment and models and parameters and product. I think that message was very, very clear in the previous presentation and it's fundamental. I will mention it definitely, but I'll try to focus on other things that we also observe that might be an issue during this change of management. So the first thing we need to keep in mind here is that many times we try to focus on zoom in basically during the commissioning, just to make sure that we align products and models and the green interconnection studies. But when we're talking about the life cycle of a project, that extends for many, many years, not only during the service part of the IBR plant, but also during the project development and sales phase. And these two phases are fundamental as well, because they will set the foundations of the plant performance that we want to have. In the project development is very important because we identify, for example, what would be the type of grid we're attempting to interconnect, what will be the potential challenges. And that's part of the grid connection application. And during the sales phase, from an OEM perspective, having a supply-only contract in most of the case in North America, that's also key for the customers and for the project, because this is the phase where we're gonna propose a technical solution to our customers in terms of capabilities of the turbines. We have turbines that are being sold globally, it's not a secret, right? But the features and the configurations that we have in a project that we sell in North America are definitely not the same that we put in UK or we put in Australia. And also the type of contracts we are contracting in US are very different, because the grid compliance responsibility in North America relies on the customer. So it's in the sales phase where we are gonna define what are the features, functionalities, configuration, etc., that this plant will have. And when we deviate from that, when we don't do the right grid interconnection studies, etc., and we deviate from that, then is when probably some of the challenges or some of the issues will arise. Then during the construction, And I will deep dive into this later on. But in the construction is a part when you are starting configuring your plan, preparing everything, making sure all the studies or the analysis you did with either with user-defined models or in terms of load flows or whatever, you make sure they are ending up in the turbine to be prepared for the test. It's very common that these exercise or these efforts are delayed, and when this happens, well, the consequence is really obvious, right? When this happens, you face challenges towards the end of the construction. You probably will fail commissioning, or you won't have a stable plan that will delay your commercial operation date, and then that will have significant financial consequences. And then service, and I know the title of this was the change of management during sales or commissioning, but also the same challenges are applicable in service. And from an OEM perspective, I think this is where we see a lot of challenges, because the construction phase will last 12 to 18 months. So between construction and commissioning, the time window is relatively short. But during service, especially nowadays that we see a lot of different work orders, new PRCs coming up, some of them having backward compatible requirements, is that where we will see or we will foresee a lot of issues popping up when there is a change of management. Because during service is where the generators owners will receive RFIs in regards to the performance of their plant or underperformance of the plant. We will see PRCs like, I don't know, PRC 28 with data monitoring, and eventually PRC 30 if there is an event in the grid that will have to report how the turbine or assets are performing, etc. So the troubleshooting and the after-sale solutions will be definitely something that is coming in the next year, because as more and more IBR connects into the grid, whatever in a specific project was agreed or sold as a cookie cutter project with a relatively strong grid and no control interactions, etc. In service, we will realize that they will require new solutions, and that will be the after-sales grid solution. In terms of the interconnection process overview, this I included this slide more for documentation purposes. It is not that relevant here, but it's just to give you an idea of the timeline. We are talking about around 5 years between the entering into the queue, publishing the TSA, and actually signing a contract, compared to the 20 years or more that a project will be during the testing and the operation and maintenance. And this is where the key will be. But it's foundational that when we are doing the grid interconnection agreement, and this is the purpose of this slide, the grid interconnection, the interconnection studies are really reflecting what we would like to see. We were talking a lot, or the previous presentation focused a lot on the modeling part, right? How was the challenge to ensure that a user-defined model and the settings of a user-defined model using an interconnection study was actually the settings that were deployed on the field. That is key, and that is only done ensuring that the interconnection studies first are using a representative model of the product. Of course, it's not a secret that we have listed for the UDM used for the interconnection studies, but it's also crucial to enhance the commissioning of a plant. In US today, Mod 26 and Mod 27 are two tests that are relatively easy to handle and pass, even with a generic model. But from Vestas, we ensure that we have a detailed commissioning internal process when we ensure that all the frequency control are working as expected, voltage control interactions, rise time, response time, etc. Because those things will eventually come in the new IEEE 2800.2 and will surface with more and more IBR connecting to the plant. So it's important also to have an internal protocol to ensure the commissioning is as expected. One thing that is very common from an OEM perspective is we are in this triangle between the developers, sometimes the generator owners or the engineering firms, and the OEMs when we start discussing about grid code. And when we look at any grid code today, or the IEEE 2800 standard, you can say that the vast majority of requirements are applicable at the point of interconnection. And it's not really straightforward to extrapolate the wind turbine performance into point of interconnection. I have so many generators owners concerned about PRC 29 and asking, show me your protection curves, and then say, yeah, I'll show you the protection curve, but that doesn't mean that that's a protection curve you have to be compliant with. It really depends on what is at the point of interconnection. Everything that is in black in this diagram is something that is project specific and will definitely affect or contribute in how the turbine response can be extrapolated to the point of interconnection. So in this game of the not game, but in this scenario of grid code requirements, it's important to know that the wind turbine, yes, it is the fundamental, or could be the solar, it is the fundamental generating a unit, but there are multiple passive components, well, sometimes also active components, that will influence in the way that the performance of the plant will be. And this is something to keep in mind, especially during the sales and the sales part of a project, because again, as I explained before, if this is not really crystal clear during the negotiation of a specific project, we will face issues like, I put some of them in the second bullet, third bullet, like long radial feeders, weak grid connections, low inertia, or even serious compensation, and also control interactions with nearby plants that are not being considered when the proposal was submitted to a specific customer, and that will deviate from the scope of a specific project. And if that is not clear when this project change hands, then the expectations will be very, very different. So I was reflecting a little bit on what could go wrong, and this is connected to the next slide, but what could go wrong when we change management on a wind farm or any IBR plant, right? And I think I could consider four main categories. The first one, I've been talking about that, and it's the early stage and specification misalignment. In Vestas, we have something called functional design specifications, and I guess other OEMs will call it in a different way. The functional design specifications is basically the overview of how the plant will be configured. This document will capture the control architecture, will capture the strength of the grid, will capture all the Vestas specific functionalities in terms of control on IBR units that plant will be required. Of course, that needs to be connected with the grid studies and the specifics of the grid. Sometimes we see a lot, and this is very common, that this is not really taken very seriously with some generator owners. Reasons could be multiple, okay? Reasons, many times it's a commercial urgency. We need to sign a project. Grid is only one small part. I know in this forum we see that grid is the vast majority of issues, but there are supply chains, there is construction, transportation. There are so many issues when we are closing a project that are really as important or more important than grid. Sometimes we see a tendency that these studies are oversimplified. That is changing, definitely, especially with the new requirements, but it wasn't the trend before. So not having that clear from the very beginning, from the very get-go, it could be an issue, definitely, when we change the management of the plant. Then the technical configuration and parameter drift. I think the previous presentation focused a lot on this. I think I won't talk too much on this. We need to ensure that we have consistent models, and this is a positive sequence. I know sometimes some people don't like to call it RMS model, positive sequence models, and EMT models. We need to also ensure that the deviations from the models that were considered to the grid interconnection studies and the as-built models are being properly captured, because when we perform the interconnection studies, just keep in mind that Vestas update their plans or they release a software update for turbines many times a year. So by the time you submit a grid interconnection study, you're running a software version that is not the one that is going to be deployed in the field. So it's very, very important to have a consistency in the firmware and of course the control architecture of the plant as was contracted. And something that's in many occasions is very difficult to capture is the conflict during the energization. We are seeing this more and more. We have a couple of projects in Canada, for example, that we were looking into because it was a relatively strong grid 10 years ago. And then from the phase 1 to the phase 2, there were at least another 6 to, I think there were 8 other IBR plants connecting to the same site. The same customer just decided to copy and paste the settings of the previous phase because everything was great. And then, the voltage start flashing like a Christmas tree because it was a relatively big wind farm. So it's very important that we will discover some control interactions. The third big bucket, I think, how much time do I have left, Julia? Sorry, I didn't start tracking the time.
You can have 10 minutes.
Okay. The third component will be the communication and handover. It's very important that we have specific protocols of handover between sales, construction, and service. Also crucial, not deviating from the functional design specifications, because any deviation will require value engineering. And sometimes we observe that the way of interpret the grid code is different between the OEM and the grid operator. This is something common. There are great places where we can have these discussions in some regions, but in some other regions in US, those discussions do not take place, and there is a single interpretation from the grid operator that sometimes is not aligned with the OEM. And then I will skip the human training and operational factors because this is just a change of staff, change of engineering consultancy firms, etc. That also will impact when there is a handover or change of management during a project. When we look at the OEM deliverables, this is kind of everything we put in the bucket or we put in the funnel here, either for the grid operator, the developer, the generator owner, the independent engineering firm, etc. So during the sales phase, we negotiate the non-standard features, the functional design specifications. We support with the grid interconnection studies, and we explain the turbines and PPC capabilities in here. It's very important because this is what is contract. In the American market, it's fundamental to understand that the supply-only contracts that as an OEM we have with the generator owners. Our responsibility is not in regards to the grid code compliance, but in terms of the performance of the generation units. The evaluation of the performance of the grid code or compliance of the grid code relies on the generator owner. So any deviation from what we actually contract will heavily impact the construction and commercial operation date. Then during the construction, we move towards having as-built models based on the generation based on the grid interconnection studies. We update the software configuration because, as I said before, during the sales phase, that could be 3-4 years before the actual construction, there was another software running for the power plant controller or for the turbines. And we start producing the first parameter verification report that is very well linked to the previous presentation, ensuring that the grid interconnection studies and the actual product on site are matching one-to-one. And this is fundamental. I know there are some markets in US that have started to ask for this. For parameter verification report, we are having that process or that protocol for every site to ensure that is not really only a deliverable towards the operator, it's only a sanity check to ensure that everything goes right. During the commissioning, that is we only support during the mod testing, and we address any deviations and plan and TVC control. But during service is where we see a lot of work coming in the next years, because we will have more and more RFIs, and this is a trend we are seeing. There are some regions in US issuing a lot of RFIs, just inquiring about why the plant did this or did that. And we will require to update more and more as-built models, because RFIs will definitely require an update on the software, and that will generate a new as-built model. The as-built model will come with a parameter verification report, and eventually with a new grid interconnection study. And when we start facing more and more challenges of integration of IBR into the system, we will start putting a lot of attention on the value engineering. Features that were not sold with the first management of the plan will have to be negotiated with the second management of the plan. I'm just trying to think on the most basic thing that maybe it's not a feature as such for reliability, but PRC28 could be a good example. That we have to capture certain data, and that is applicable to every site that we have out there. So OEMs will have to figure out how to capture that data. If tomorrow there is a new requirement, or we can think about the NOGA 245 as another example, right? That every plant needs to be compliant with some requirements. If they didn't file an exemption, then we'll have to add some value engineering there to have a different offer for the market. And then this is of course linked to the bubble below, that is the grid requirement. So if we don't have a clear path between sales to service, and we change management during this phase, there could arise some conflicts, because Vestas, and I would assume most of the OEMs in this call or in the industry in the US, have supply only contracts, and their responsibility ends to what has been contracted, with a snapshot or a static picture of the requirements by the time we enter into a contract. So just to wrap up the presentation, we need to have a rigorous electrical design. We cannot oversimplify the grid interconnection studies at the beginning. We need to go a bit beyond that. I know that in some regions the bar might not be super high, in some others it's really high, but I think we need to have that consistency. Otherwise, we will have conflicts during the construction and service. It's just that we will pass it to the next owner of the plant, or we'll have to deal with them during service. Coordination is very, very important. The OEM coordination with the generator owner, with the grid operator, and the independent engineering firm is crucial to ensure that we understand the functionalities of the product that we are installing inside, and that product actually represent what is going to be deployed, that the models already represent what is going to be deployed on site. And finally, I would like to emphasize on something that we see that is going to happen a lot, and is that documentation is not properly stored and kept for many of the projects we have, or at least I have encountered in the US. In many occasions, none of the work that we have done from very early sales to the final stage of service is not properly documented. Models are not being stored. There is no version control on the software that consultants or generators owners have used to perform studies. Everything ends up in a couple of print screens in a report. Nobody really knows what is actually deployed on site and what are the actual settings in the turbine. So consistency in the documentation is key, because in the next years we will see a lot of changes in plants that are in operation, and we will have to, everyone in the industry must have a clear baseline where we are starting from in order to make the necessary changes to move to the next phase. I will I'll stop here. Julia, I think I have, yeah, like another 10 minutes that I could speak about this, but I'll stop here.
Right, thank you, Miguel.
No problem.
All right, thanks so much. We'll go ahead and switch gears to Patrick, who will talk about how it all hangs together, kind of between OEM and developer as the projects are being actually built and implemented. So go ahead and get started. And again, while Pat is sharing his screen, please put your questions in Slido with event code Slido7. Oh, sorry, first 7.
All right, is that coming through okay?
Yes.
All right. I think am I sharing the Slido or am I? No, okay, never mind.
No,
All
I
right.
see your screen full screen. Yeah, with the
Excellent.
presentation.
Excellent. All right. So I'm Patrick Hart. I work for Mortenson. So this presentation is going to focus primarily on this topic from the EPC perspective. We'll look at this from the commissioning angle and the items to look for when ownership changes hands before the facility reaches its commercial operation date. The goal, I think, is to provide prospective buyers and sellers help them like understand what compliance means during this transition, and then how to avoid some of the risks that would delay COD or trigger regulatory penalties along the way. Before I go too far, I want to talk a little bit about Mortenson. EPC stands for Engineering, Procurement, and Construction. Sometimes I joke with, not joke, but like that last C can stand for commissioning for us. Because we spend a lot of time focusing on that particular point, and through this presentation you might understand why. At a high level, we've delivered over 270 wind projects, 100 solar projects, 40 plus energy storage projects across the US. Our experience generally spans decades, and we really actively collaborate with our developers and OEMs to design solutions that improve the project outcomes, right? So compliance with the grid codes and the interconnection agreements is a huge focus for us, and that's really what spells success in the end, right? Getting the project across that COD finish line. All right, so I'm going to start real quick. I want to touch quickly on the pre and post COD transitions. Largely, what you look for is going to be the same, right? The primary difference is that post-COD facilities, while operational, are not always guaranteed to be compliant, right? In fact, it's actually very likely that upgrades will be necessary to address upcoming regulatory requirements. You can't expect that a post-COD facility is going to be compliant, and depending on what changes are required, this might require an expensive adventure to kind of get you there. On the flip side, when the ownership changes before COD, the facility is still in the commissioning or pre-commissioning stages. And many of the settings that drive compliance with those requirements are evolving. This provides essentially the potential buyer with an opportunity to address any potential issues that might show up before they become too expensive to do so. Generally, from a commissioning point of view, you want to focus on understanding the project-specific requirements, right? Review that IA, the LGIA, and any existing exemptions, right? These dictate effectively what that facility must deliver to the grid operator. As Miguel mentioned earlier, documentation is absolutely critical, right? Gather commissioning plans, test results, any compliance certificates. Missing documentation will delay the interconnection approval probably, or cause problems to show up in the later stages of commissioning. And when that happens, right, at the very end of the projects, that's when those delays are very costly, right? Problems are more difficult to fix at that stage. So that's something you really, really want to avoid. Identify any potential gaps early, right? Hardware, firmware, software changes might need to be updated in order to meet those latest standards. Metering locations and communication protocols can also be limiting factors. That's actually, to be honest, a good chunk of where I spend my time. just making sure that the stuff that we're putting on the grid or into one of these projects will actually allow the facility to hit the speed of response and performance requirements that are coming down the line, right? So pre-COD transitions often will involve more work. They include schedule risk because anything that you do to delay COD is going to cost you money. But they generally will allow you to transition that facility and align it with your long-term business goals. I think post-COD transitions may seem easier, but I again don't assume that there's going to be compliance. Verify everything independently, and then don't take anything for granted there. All right. So compliance generally impacts your financial performance. If the equipment isn't really designed for profit, you're going to face unexpected costs later. I would first determine the IBR OEM compliance. Essentially, all those things that we were talking about, those parameter settings, ride-through capabilities, reactive power performance, protective relay settings of the balance of plant. I would say equipment procured earlier on may not meet newer NERC or IEEE requirements, right? So if the project is kind of been a couple years in the making, it's possible that the equipment that was purchased early is not going to actually be compliant, right? Replacing that equipment is going to be expensive. So do your due diligence there before you agree to anything there. Operationally, facilities are becoming extremely complex, right? We're seeing multi-phase, we're seeing hybrids, we're seeing co-located resources, all becoming relatively common. I can't express how important it is to get that strong control narrative in place, right? Mortenson, actually, that's a document that we require every single one of our projects to develop if it's not existing already. And it effectively defines essentially the control strategy for each of these projects, right? What does this facility consist of? How does the equipment satisfy essentially the goals of those interconnection agreements? And like what are the different services that it provides, and how does it provide those services? I would also include collecting other critical documentation, saying commissioning test plans. Depending on how far within the commissioning process it is, those tests might have already been performed. If those are already completed, get the results from those as well. Operation manuals, maintenance guides, all that kind of stuff you need to find up front. Finally, as if you're going to be buying a facility, you're going to look at trying to make money on this, right? So another thing I would look at is verifying the ratings of the equipment, look at your degradation estimates and capacity factors. For storage facilities, you probably want to review the energy and power overbuild and the expected derating conditions. Another topic was augmentation. I would say ask if the option exists and if the site was designed for it. Often an OEM will tell you, yes, it's possible. And then you go and look at the site design and it's not been accounted for in the site layout. So just making sure that if you're going to have to build out to keep that kind of energy capacity available throughout the life of the project, you kind of look into those topics as well. And then I would say finally, if there's any operational runtime, if it's in a commissioning phase where you actually see how the system's running, I'd ask for operational data. First off, does that data exist? Look at equipment uptime, fault performances, any reoccurring issues like HVAC or power module failures, anything that would indicate that those units, or there's like a problem unit somewhere that needs to be addressed. I think that wraps it up for this slide. So I think we'll kind of wrap up this. We'll be pretty quick on this presentation, so I think we'll collect some of the time back. But I want to kind of do a high-level recap. Really perform a compliance gap analysis. I think that's probably the most important thing. So compare the facility against the NERC and IEEE standards. the ones that exist today and the ones that are actually coming down the line, because those are all available to read and see what are going to be future requirements that we're going to be enforcing here in the States. If you need to, I would hire an IE to support you kind of in that process. Another topic I didn't actually hit earlier, but it's stricter requirements around cybersecurity are on their way, right? So make sure that the equipment and the service providers are either compliant at this point or can be made compliant in the future without completely redesigning your entire IT infrastructure that's on site, because that can be extremely disruptive both to operation and the design. I'd say know your equipment, right? If you're going buy a project, engage those OEMs really early, especially if that IBR technology is not something that you've worked with before. Secure the dynamic models and confirm the firmware settings of your IBR facilities match the designs that are modeled. If the updates are needed, plan for that as early as possible in the commissioning process. Delaying that's going to delay your COD and the potential financial impacts associated with that. I would say engage the EPC early. In pre-COD transitions, your EPC is really an ally, right? We're here to help maintain that schedule integrity, ensure the compliance during commissioning. Really rely on EPCs, rely on us for that kind of support. And then I would say plan for the upgrades, right? If hardware can't meet the requirements and the exceptions are not possible, because that is an option sometimes, I would budget for the replacements of that hardware or the control systems that support that control narrative that needs to be there. And then those actions have the potential to protect your COD timeline. I mean, if you're replacing inverter equipment, that's a pretty hard hit. And try to avoid that, but it's possible that a firmware update or something will help address any of the changes in compliance needs. All right, I think that generally wraps things up from my side. Julia, if you want, I can hand it back to you. And thank you for having me.
All right. Thanks so much, and thanks for catching up some time. We have a lot of questions.
My pleasure.
Yeah, lots of questions here, and I have a couple just for structured discussion. So we'll see how far we can go. But you still, sharing is not sharing anymore.
Sorry.
Yeah, so I'll take questions one by one. A lot of questions were to AES, but Miguel, Pat, feel free to jump in if you have anything to add. So let's make it more interactive this way. The first one is to AES, your inverter life